students, welcome to Sunil's tutorial. I am Sunil Milwani and today we will be doing this chapter called as Kinetic Theory of Gases. Let's see what do we mean by internal latent heat. First of all, let's understand what is latent heat. Let's try to understand what do we mean by latent heat. Now latent heat, for example, let's consider that I have ice. Ice is at 0 degrees Celsius. Let's assume I heat ice. I'll get water, right? This is ice, this is water. What will be the temperature of this water? The temperature of this water will be 0 degrees only. Question, sir, where did all the heat go? The heat was used to convert ice from solid state to liquid state, right? The amount of heat required to convert a unit mass into liquid state at its melting point is called as latent heat of fusion, right? So what is latent heat? Now when we talk about latent heat is the amount of heat required to convert a substance from one state to another state, okay? Now, latent heat of fusion. Quantity of heat required to convert unit mass of solid into liquid state at melting point without change in temperature. That is what is latent heat of fusion. Fine, do we understand this? The amount of heat required to convert unit mass of ice into unit mass of water without changing the temperature is called as latent heat of fusion. Now I could do the same thing with liquid and gas. I could have, say, liquid here, right? Unit mass of liquid at 100 degrees Celsius, right? I heat this, I'll get steam, right? So the amount of heat required to convert liquid to steam is called as latent heat of vaporization. So what is latent heat of vaporization? Latent heat of vaporization is the quantity of heat required to convert unit mass of liquid into gaseous state at boiling point without change in temperature is called latent heat of vaporization. Fine, do we understand this? Next. Now, so we know what is latent heat of fusion. It is the amount of heat required to convert from one form. Latent heat is the amount of heat required to convert from one state to another state. You can have latent heat of fusion and you can have latent heat of vaporization, right? Now, there exists some intermolecular force of attraction between the molecules of substance at any state. The intermolecular distance in the liquid is greater than that in the solids, and those in gaseous is still greater. Hence, during the change from solid to liquid, some work has to be done against the intermolecular forces to increase the distance between them, right? At the same time, there is an increase in the volume When you heat any substance, there's an increase in the volume due to the change in form, right? So during such expansion, some external work also has to be done. Some internal work has to be done to increase the intermolecular space. Some external work has to be done to increase the volume. Thus, I can say that the part of latent heat is used to perform internal work against the intermolecular forces of attraction, so that you can increase the separation between them, and the remaining part of the heat is absorbed to perform external work for expansion of the substance, right? So that this is how latent heat is used, right? I can say that latent heat there exists intermolecular forces of attraction. There exists intermolecular forces of attraction between molecules of a substance in any state. Substance in any state, right? The intermolecular distance in liquids is greater. The intermolecular distance in liquids is greater in the case of solids. Right? And similarly, in the case of gases, it is still greater. In the case of gases, it is still greater. Fine. So in that case, I can say that hence during a change of state, the change from solid to liquid, hence during a change from solid to liquid or from liquid to gas, work is required to be done against the intermolecular forces of attraction. Work is required to be done against the intermolecular forces of attraction. Work is required to be done against the intermolecular forces of attraction so as to increase the separation, right? To increase the separation between the molecules. Right? Moreover, there is an increase in the volume of the substance There's an increase in the volume of the substance when during the change of state. Right? Thus, during expansion of the substance, some external work has to be done. During such expansion, the substance has to perform some external work. Substance has to perform some external work. Therefore, I can say that a part of the latent heat is used by the substance A part of the latent heat is used by the substance to perform internal work against the intermolecular forces of attraction. Right? And against the intermolecular forces of attraction to increase the separation between the molecules. I can also say that the remaining part of the heat is used or is absorbed. The remaining part of the heat is absorbed and is used to perform external work. During expansion. Right? So from this discussion we can come up with the equation that we can therefore say that latent heat L is equal to Li plus Le, where Li is the latent heat for internal work. Latent heat for internal work, and Le is the latent heat for expansion or for external work. Right? Now, if P is the external pressure and dV is the change in volume, if P is the external pressure and dV is the change in volume, in that case I can therefore say that external latent heat is P dV. External latent heat is nothing but pressure into change in volume. Thus I can therefore say that latent heat is internal latent heat plus P dV. Right? Now, in order to represent this in mechanical units, I can therefore say that L is equal to Li plus P dV upon J, right, where J is the mechanical equivalent of heat, Fine, do you get this in here? Now, what will be the SI units? So this is my equation for latent heat. Now, what will be my SI units for latent heat? SI units of latent heat will be, what is latent heat? Latent heat is the amount of, is the heat required to convert unit mass. So it is heat joules per kg, right? The dimensions, definition, it will be nothing but the dimensions of heat upon dimensions of mass. So this is going to be nothing but m1 L2 T minus 2 upon m1. m0 L2 t minus 2. Right? Next, let's see numericals based on kinetic theory. Take down the numericals, please. Calculate the average velocity. Calculate the average velocity, the mean square velocity. Calculate the average velocity, the mean square velocity, and the root mean square velocity of 5 gas molecules having velocities of 5 gas molecules having velocities 6 meters per second, 2 meters per second, 4 meters per second, 5 meters per second, and 3 meters per second. Having velocities 6 meters per second, 2 meters per second, 4 meters per second, 5 meters per second, and 3 meters per second. Fine, do we get this? Now, let's see this. Now, first let's find out the average velocity. Let's first find out the average velocity. Average velocity C bar is nothing but C1 plus C2 plus C3 plus C4 plus C5 upon 5. That will be my average velocity. Next, mean square velocity. Mean square velocity is going to be nothing but C bar square is C1 square plus C2 square plus C3 square plus C4 square plus C5 square upon 5. And last, root mean square velocity is square root of mean square velocity. Whatever answer you get for mean square velocity, take square root of that, you should get the answer. The answer for this sum should be average velocity is 4 meters per second, mean square velocity is 18 meters square per second square, and the root mean square velocity is 4.24 meters per second. Right? Take down next sum, please. Calculate the RMS velocity. Calculate the RMS velocity of oxygen. Calculate the RMS velocity of hydrogen. Calculate the RMS velocity of hydrogen at MTP if the density of hydrogen is 0.09 kgs per meter cube and pressure is 1.013 into 10 raised to 5 newtons per meter square. Now, RMS velocity is given by the formula 3p by rho. You have both the values p and rho. You can substitute and get the answer. The answer for this sum should be 1838 meters per second. Next, take down next sum, please. Calculate the RMS velocity of oxygen. Calculate the RMS velocity of oxygen at 127 degrees Celsius at 127 degrees Celsius if the density of oxygen at NTP, if the density of oxygen at NTP is 1.44 kgs per meter cube and pressure is 1.013 into 10 raised to 5 newtons per meter square. Now first of all, let C0 be the RMS velocity. Let C0 be the RMS velocity of oxygen at NTP. Now, the RMS velocity at NTP is given by the formula. I can say that C is going to be equal to square root of 3p by rho. So that will be my C0. C0 will be nothing but square root of 3p by rho. P is given to me, rho is given to me. Now, you will say let C1 be the RMS velocity of oxygen at T degree K, right? So temperature is given to you. Now we know that RMS velocity is directly proportional to square root of temperature. Therefore I can say that C0 upon C1 is square root of T0 upon T1. Now C0 was the RMS velocity at NTP. Since it was the RMS velocity at NTP, T0 will be 273 degree Kelvin. NTP is normal temperature and pressure. Normal temperature is 273 degree Kelvin. Right? Next, the answer for this sum should be 556.1 meters per second. That should be the RMS velocity at 127 degrees Celsius, or which would work out to be 400 degree Kelvin. Right? Next, next sum please. Find the temperature at which the RMS velocity of gas will be thrice its value at NTP. Right? So that means they've given you CT is thrice C0, where I can say CT is RMS velocity at T degree K and C0 is RMS velocity at NTP. Now since C0 is the RMS velocity at NTP, therefore I can say that T0 will be 273 degree Kelvin. Now we know that C is directly proportional to square root of T. Therefore I can say that C0 upon CT is square root of T0 upon T. The only unknown in this case is going to be T. Right? So when you solve this, you should get this answer. You will get this answer as T will come to 2184 degrees Celsius. Next, take down next one please. Compare the RMS velocity of hydrogen. At 400 Kelvin with RMS velocity of oxygen at 900 Kelvin. With RMS velocity of oxygen at 900 Kelvin. Now RMS velocity is also equal to 3 RT upon m, right? Therefore I can say that RMS velocity is directly proportional to square root of T upon m, right? That means I can say that RMS velocity of hydrogen upon RMS velocity of oxygen will be equal to square root of temperature of hydrogen upon temperature of oxygen into mass of oxygen upon mass of hydrogen, right? That is your molecular weight. Now, but we know that molecular weight of oxygen is nothing but 32 and molecular weight of hydrogen is 2. So substitute these values, you should get the answer. The answer for this sum should be 8 upon 3. Next, take the next one please. The RMS velocity of oxygen, at 0 degrees Celsius, the RMS velocity of oxygen at 0 degrees Celsius, the RMS velocity of oxygen at 0 degrees Celsius is 460.4 meters per second. 460.4 meters per second. Find the RMS velocity of hydrogen. Find the RMS velocity of hydrogen at the same temperature. Find the RMS velocity of hydrogen at the same temperature if the molecular weight of oxygen and hydrogen, if the molecular weight of oxygen and hydrogen is 32 and 2. Right? Now we know that RMS velocity is square root of 3 RT upon m. Since temperature is constant, therefore I can say that RMS velocity is inversely proportional to square root of m. Therefore I can say RMS velocity of oxygen upon RMS velocity of hydrogen is equal to square root of molecular weight of hydrogen upon molecular weight of oxygen. Right? Now, once you have this, you can substitute the values. You have molecular weight and you know the molecular RMS velocity of oxygen. Right? So you will get the answer for this sum should be RMS velocity of hydrogen is 1841.6 meters per second. Next, take on next up please. At what temperature will oxygen molecules have the same RMS velocity as helium molecules at 127 degrees Celsius. We know that RMS velocity is nothing but square root of 3 RT upon m. Therefore I can say that RMS velocity of oxygen to RMS velocity of helium is going to be square root of temperature of oxygen to temperature of helium into molecular weight of helium upon molecular weight of oxygen. Right? So in this case, I can say that they've given you that, but it is given to you that RMS velocity of oxygen is the same as RMS velocity of helium. Therefore, you will get 1 is equal to square root of temperature of oxygen to temperature of helium into molecular weight of helium to molecular weight of oxygen, right? Now out of which we know that molecular weight of helium is 4 and molecular weight of oxygen is 32. Temperature of helium is given to you. You should be able to get the temperature of oxygen. Fine. The answer for this sum, you'll have to square both the sides here, guys. So you will get 1 is equal to T0. THE is equal to MHE upon M0. Right? Now you can cross multiply and you will get your answer. You want to find out temperature of oxygen. So you can say temperature of oxygen is temperature of helium into molecular weight of oxygen upon molecular weight of helium. Right? The answer for this sum should come out to 2927 degrees Celsius. Next, take down next one please. Calculate the number of molecules. Calculate the number of molecules in 1 liter of gas. Calculate the number of molecules in 1 liter of gas at NTP at 1 liter of gas at NTP. That means temperature is going to be 273 degree Kelvin, right? And pressure is going to be 1 atmosphere, that's 1.013 into 10 raised to 5 newtons per meter square. Since they give you NTP, this is your normal temperature, normal pressure. So calculate the number of molecules in 1 liter of gas at NTP if the mass of each molecule is 4.55, if the mass of each molecule is 4.55 into 10 raised to minus 25 kgs, and the RMS velocity at NTP is 360 meters per second. Is 360 meters per second. Pressure formula. Pressure is 1/3 nmc square upon V. You want to find N. So thrice PV upon mc square will give you the number of molecules in 1 liter of gas. You should get this answer as 5.154 into 10 raised to 21. These many molecules are present in 1 liter of gas. Next, take our next one please. Determine the pressure. Determine the pressure of 4 grams. Determine the pressure of 4 grams of hydrogen occupying 16 liters at 10 degrees Celsius, occupying 16 liters at 10 degrees Celsius if R is 8.315, if R is 8.315 joules per mole Kelvin, and the molecular weight of hydrogen is 2. And the molecular weight of hydrogen is 2. right? First of all, let us find out the number of moles. Number of moles is weight upon molecular weight. Weight is 4 upon molecular weight is 2. So number of moles is 2. Once you have this, then I can say gases law. Gases law says that PV is equal to nRT. What I need to find out is P. So this is going to be nothing but nRT by V. N I know, RT and V I know. I should be able to get the pressure. Answer for this sum should be 2.914 into 10 raised to 5 newtons per meter square. Next, take on next sum please. Determine the value of universal gas constant. Determine the value of universal gas constant. Determine the value of universal gas constant if the pressure exerted by 4.032 grams of hydrogen occupying 16.8 liters at 0 degrees Celsius at 0 degrees Celsius 0 degrees Celsius at 0 plus 273 degree Kelvin at 0 degrees Celsius is 2.703 into 10 raised to 5 newtons per meter square. The molecular weight of hydrogen is 2. The molecular weight of hydrogen is 2. Now, let's see this. I can use gases law. I can say by gases law states that PV is equal to nRT. PV is equal to N is weight upon molecular weight, RT. Therefore, I can say that R is nothing but PVM upon MT. You have all the values, you can substitute and get the answer. The answer for this sum should be 8.251 joules per mole Kelvin. Next, take on next sum please. Find the mass of 10 centimeter cube of gas. Find the mass of 10 centimeter cube of gas at NTP if the RMS velocity of gas is 400 meters per second and the atmospheric pressure is 1.013 into 10 raised to 6 newtons per meter square. First of all, I can say that RMS velocity is square root of 3p by density. Squaring both the sides, I can say c square is 3p by rho. Therefore, I can say density is 3p upon c square. Now, density is nothing but mass upon volume, right? Where here, in this case, density is the mass per unit volume. Density is mass per unit volume. Volume is given to you, so I can get the mass. Density is nothing but mass upon volume. Density you found out is nothing but 3p upon c square. Mass we do not know. Volume is given to us. V is given to you. So 3pv upon c square will give you the mass. That will tell you what will be the mass occupied by 10 centimeter cube of gas. Next, take on next up please. A cylinder is filled with hydrogen. A cylinder is filled with hydrogen at 500 Kelvin and exerts a pressure of 1 atmosphere. If hydrogen is replaced by helium, if hydrogen is replaced by helium of equal mass and same temperature, what will be the pressure exerted by helium what will be the pressure if it is replaced by helium of equal mass at the same temperature? What will be the pressure exerted by helium and what is the relative number of molecules? What is the relative number of molecules of hydrogen and helium? Now guys, we know that pressure is equal to 1 upon 3 mc square by v, right? Now, as the masses and volume is same, they are saying that the same cylinder is filled, that means the volume is same and same mass is given to you. As mass and volume is same, therefore I can say that P1 upon P2, mass is same, volume is same. 3 will get cancelled, so it will be C1 square upon C2 square. Right? Since they are at same temperature, since the temperature is same, at same temperature they will possess the same kinetic energy. Therefore, I can say that kinetic energy per molecule for both the gases is same. That means half m1 c1 square is half m2 c2 square. Kinetic energy will be same. Half and half gets cancelled. So in which case I will get c1 square upon c2 square is m2 upon m1. Let's call this as equation 2. Let's call this as equation 1. So if I equate equation 1 and 2, I can say that equating equation 1 and 2, you can say that P1 upon P2 is M2 upon M1, right? But M2 upon M1 is nothing but molecular weight of 2 upon molecular weight of 1, right? Therefore, I can say that P1 upon P2 is M2 upon M1. Now the gases that are used are hydrogen and helium, right? Helium, molecular weight, but molecular weight of hydrogen is 2, molecular weight of helium is 4. Therefore, P1 upon P2 is going to be 4 upon 2, that is 2. But I presume P1 is given to you, right? So in that case, I can say that P1 is given to you as 1 atmosphere, I presume. Yeah. So I can say 1 upon P2 is equal to 2, therefore P2 will be 2 atmosphere. So the pressure exerted by helium will be 2 atmosphere.
So half atmosphere.
Half atmosphere. Half atmosphere. Right? Now, once you have this, then I can say that they've also said that as the mass of each gas is same, as the mass of each gas is same, they are fitted in the same cylinder. Therefore, mass of the gas, one molecule multiplied by the number of molecules, should be mass of the other gas multiplied by the number of the other molecules. Therefore, I can say that N1 upon N2 is going to be equal to M2 upon M1, which is nothing but M2 upon M1, which is nothing but 4 upon 2, which is 2. So the relative number of molecules of N1 to N2 is going to be equal to 2. Next, take on next one please. Calculate the specific heat. Calculate the specific heat of gas at constant volume. Calculate the specific heat of gas at constant volume if the density of gas is 19 into 10 raised to minus 2 kgs per meter cube. Cp upon Cv is 1.4. J is 4.2 into 10 raised to 3 joules per kilocalorie, and atmospheric pressure is 1.013 into 10 raised to 5 newtons per meter square. Right? And temperature is 273 Kelvin.
What is J?
Mechanical equivalent of heat. Now we've derived this formula that for principal specific heat, Cp minus Cv is nothing but R upon Mj. We've done this derivation, right? Also, I can say for 1 mole of gas, by gases law, PV is equal to RT, right? Now, I could also say that density is mass upon volume. Therefore, I could say that volume is mass upon density. Once I know the value of volume, I can substitute this value of V in M upon rho. I can say that Cp minus Cv I could say that PV is equal to PM upon rho, multiply both sides by P. V is equal to M upon rho, multiply both sides by P. So I'll get PV is equal to PM upon rho. But PV is nothing but RT. Therefore I'll get RT is nothing but PM upon rho. Right? So in that case I can say that R upon M, if I cross multiply, R upon M is P upon rho T. Right? R upon M in the principal specific heat equation can be substituted. If I substitute this in the principal specific heat equation, I'll get Cp minus Cv is equal to R upon M, can be written as P rho T into 1 upon J P rho T. I know 1 upon J, yes, M is not there. So I can find this out. Now Cp minus Cv, I can say, but Cp upon Cv is given to you as 1.4. Therefore, I can say that Cp is 1.4 Cv. I can substitute this value, in which case I'll get 1.4 Cv minus Cv is P upon rho Tj. Right? Now you should be able to find the answer. When you solve this equation, you should get the answer as Cv will come out to be 1.162 kilocalories per kg Kelvin. Right? Okay, we'll stop this here for the day. Thank you very much.